Okay, let's examine another example where we're attempting to graph the equation for a rational function. And this will also be helpful when considering activities like the paired work that we were doing in class, or the speed dating of rational functions. So let's consider the following. F of x is equal to these two quantities multiplied together divided by the product of these two quantities. Okay. So when attempting to graph these things, it became very clear to me that we're quite accustomed to looking for the VAs, and second to that, the zeros. So why don't we begin with looking at the zeros? Okay. So take note that the zeros do occur at the factors that are in the denominator. So we have x plus 3 equaling 0, or x minus 4 equaling 0. So it tells us that the zeros are at x equal minus 3 or at x equal 4. Another consideration that we had as well with graphing was the vertical asymptotes. And recall, this is where values of x make the factors in the denominator equal to 0. So in this case, we can eyeball them. They would be at x equals plus or minus 2. Now also take note that I've been using the word factor. You might see in some examples where the polynomial that's given is not in a factored form. So I want to make that note right here that in many cases, in order to extract the information, you would need to factor. Okay, so now that we have that information before us, why don't we go ahead and begin sketching a graph of the function. So let's plot the information that we do have so far. So we have our zeros and our VAs. So if we place our VAs equally distant from each other, that's at minus 2 and 2. And then we'll also plot our zeros. So our zeros again are at minus 3 and 4. So let's add a dashed line or a trend line just to indicate where those VAs happen to be. And we'll just copy and paste this right here. Perfect. Okay. Well, now that that's all set into place, it might be to our benefit to begin thinking about where the graph of the function will be. Or, like we saw in class the day before, where exactly the function won't be occurring. So let's set up an interval table that we can use to study this function. So I'm going to go with a 5 by 5 table. I believe that should be adequate. And the reason being is if we go back, take note that we're going to have several intervals being studied. Okay, so we're going to have from here to here, from the 0 to the VA, the span of the domain between the VAs, between the VA and the 0, and then beyond that. So each of these intervals need to be accounted for in our table, and if we count them up, there are 5 of them. Note that when the word critical value is used, that's being used in the context of zeros and the VAs. Okay, so let's go ahead and fill this out. So according to the information we have a 0 at x equals -3. So let's go less than -3. Let's also go between -3 and -2. In between the two VAs, between the 0, that is the next 0, and the VA. And we are short 1 row, as we do require a column to list the various factors. So we'll draw an extra one in, and then x bigger than 4. Over in the left-hand column, we'll have to add another row as well. So we have factors x plus 3, x minus 4, x minus 2, x plus 2, and below that we'll have the sign of the quotient. So let's go ahead and begin filling out the table. We'll deal with the first 2 intervals, then we'll go back and we'll examine the graph for where those pieces of the function should be occurring. So if we test a value such as -4, okay, so let's test -4, or f at -4, and see what that's going to produce. We'll take note that the signs are going to be negative all the way through, meaning that the quotient is going to be positive. Okay, let's tackle one more interval and see what we come up with. So from -3 to -2, we could very well look at -2.5. And if we test each of those intervals, we'll end up with a positive, a negative, and followed by another negative. Now the quotient of 3 positives and the negative are going to produce an interval where the y values are negative. So let's go back to the graph and let's highlight the areas where we expect not to see a function or the part of the function occurring. So I'm just going to get rid of these notations here. I don't think we need them at this point in time. And we'll check our running time on our video. We're at 7 minutes and 57 seconds. We'll run this for nearly 15 minutes. So using some highlighter, let's take care of the areas that we know the function will not be occurring. So let's start with the area that is left of the first 0. So let's highlight that region. So the function there cannot be negative. Over the next interval between -2, -3 and -2, the function cannot be positive. So we'll highlight this region. So this begins to give us a good idea of where the graph of the function is going to occur. We might even go so far as to begin sketching the function. So the graph of the function must be negative between the 0 and the VA of -2. So what we're going to see is an interval of decrease here. And then to the left of the 0, the function's going to pass through, but as to its behavior, we're going to have to do an extremity test to verify where that graph is going to end up going. And that's our next step. So let's see if we can't conduct an extremity test to complete that portion of the graph. So we are at step number, let's check here, 1, 2. This would have been step 3. Here we go, step 4, our extremity test. So let's look at the end behavior. for values that are less than -3. So what we'll do is we'll set up a very simple t-chart and we'll test values. So at 0, we had -3. Oops. That's the other way around. At the 0, -3, we had a value of 0. If we test other values, I'm just going to work with powers of 10, say -10, -100, -1,000, and we'll just keep on going to some infinitely large negative value. Let's see what happens to the y values of the function. So for instance, over here, if I were just to use this as a scratch pad, well, let's determine the value of f at -10. So if we substitute that back into the factored form of the equation and evaluate, we'll have our y value. Okay, so it follows that the first quantity is -7, the second is -14, and in the bottom -12 and -8. Put all of that together or do some canceling before the final answer, I think you'll find that you'll get approximately 1.02. Okay, so let's add that back to the table, and then we'll move forward from there. If, in like manner, you evaluate with x being the other values, you should get approximately 1.01. At -1,000, if we carry a few more decimal places, you're going to see the following. And if we continue the same pattern,
Please, any staff member who has not yet had their photo taken, you can go to the library now, please. Any staff member who has not yet had their photo taken or would like to retake, you can go to the library now, please.
the function will get closer and closer until it approaches +1. So what this implies is that our horizontal asymptote will be y equals 1. And what we'll do later on is we'll come back and do another test to show that the horizontal asymptote is in fact at +1. So let's go back and add in our horizontal asymptote, and we'll use a slightly different color for that. Let's see now. Let's put an arrow on the end of that. Perfect. And now we can complete the graph function, at least for this interval. Okay, so we'll end that part of the video here and we'll pick it up again in a second segment. This is a rather lengthy solution to justify the graph. I'm sketching it by hand.